Hi, I'm going to teach you a part of calculus which is finding the derivative of functions. So here we're going to use the power rule to find derivatives. So I've written here a function f of x equals 3x to the fourth. Now we're going to find the derivative of this. Before we do, I'm just going to show you some notation. So this is one way to write derivative once you got it. And we say the letters dy dx. So that's how we would say this. So we will have like dy dx equals whatever the derivative is, and we'll just put it on the right hand side. Or you can write it like this, which we will say f prime of x. So we just have f prime of x equals whatever, blah blah blah. Or this way, y prime is the way we say this. So we can have y prime, we can have f prime of x, or just dy dx. We're going to use this one for now. So here's a derivative of the function 3x to the fourth. So we've got f prime of x equals 12x to the third. Now how do we get here? Let's rewrite this function. So I'm going to have f of x equals 3x to the fourth. Okay. Now to find the derivative, what we're going to do is look here first, this number. Now that number we will say it's a constant. It's just a constant number that's there. It's just being multiplied out. This is not going to change anything unless you're going to multiply something out when you do the power rule. So when we just have a number hanging out, it's not really attached to the x, right? We can imagine the x being in parentheses and the x is being raised to the fourth. The 3 isn't being raised to the fourth. 3 is just out there. This could have been a 2. It could have been nothing. It could have just been 1. 1 times x to the fourth. It would have just been x to the fourth. So at first, we just put the constant out there. And let's just write in parentheses so we can separate it from everything. So next, there's x to the fourth, that part. So you see this number here? All we're going to do is literally bring it down. So whatever's being raised in the parentheses, this could be x, this could be multiple things, this could be cosine, log, whatever. It's being raised to something. So the first thing you do is whatever number is being raised to, you bring that all the way down. So you just literally bring it down. So when we bring it down, what does that mean? That means we're multiplying it out by any number that's already out there. That constant we brought out there, we're going to multiply it by 4 because 4 is what we brought down. So we can multiply it out later. We don't worry about it right now. You see, that's why I said it could affect it if it's being multiplied out. But in any case, it just stays there. Next. Once we brought down the exponent, whatever is on the inside, the base that's being raised, whatever this is, it doesn't matter what this is, a smiley face, whatever that exact thing is, we're going to write it over. Okay, so just literally write it over. Next, the final thing, whatever number the exponent is, whatever that is, all we're going to do is subtract by 1. So let me just write 4 minus 1 is obviously 3. So what we're going to do is we're going to forget about this number and we're going to replace it by the number we subtracted by. We're going to replace that in a derivative. So we have x to the fourth. So once you subtract by 1, we get 3. So it's going to be whatever that is, you put the exact same thing here, and you raise it by your exponent minus 1, which is 3. So we're done. So all we have to do now is just simplify. 3 times 4 is 12, and x to the third, which is what I had here. So let's do another one real quick to show you. What if there wasn't a number in front? What if it was just, think of, if there's no number, just think of 1 being there. So 1 times whatever. So let's just do x to the 5th. That's it, x to the 5th. So the derivative, let's use dy dx now. The derivative is, if there's a 1 here, you can think of it as a 1. You don't have to. You could just, the 1 is not going to do anything. But just for now, let's just imagine there's a 1. So our exponent, we just literally bring it down. So we just write 5. Whatever's on the base, you write that again. It doesn't matter what it is. You write the exact base down. 5, you subtract it by 1, and that's what you're going to put here. Whatever you're raising it to, that exact same thing, all you have to do is subtract it by 1, and you go back to your base and you write it there. So now the answer is just 5x fourth. Now you could have skipped this right here. If there's no number, you just start off from here, you bring it down, 5, subtract by 1, so you write x to the 4th, and you're done. Okay? So another final one, I'll just show you how this is easy. X squared. So the derivative is, there's a 1 here, so it really doesn't matter. You don't have to write it over once you get used to it. Bring your exponent down, so that's 2. Whatever's in here, imagine there's parentheses, all being raised to a 2. You write that exact same thing. So you write x, subtract by 1, so it's all raised to the first. So anything raised to the first is the same thing, so you can also write 2x as your answer. So let's look at this. F of x equals x squared, and the derivative, f prime, is 2x. So how does this relate? What is this? What is this prime? Now I'm going to show you in terms of a graph. Now, the way you draw x squared is like this, right? Now, we all know that this is the positive side, and this is the negative side. All of this is positive and negative, and imagine this is 0. Imagine over here we have 1, we have about -1 around there, then it just goes on. We could have 2, and here it'd just be 1. If it was here, it'd probably be 4. So we just skipped a few numbers. Alright, so this is just the function. I'm going to write here what the function is. This is the original function, x squared. Now we said the derivative is 2x. But what does that mean? So let's look in terms here, what the function is doing, right? So let's draw little lines here. If the function is increasing, it would obviously go like this. Or it could increase as a curve, or it could just be increasing like this. If it's decreasing, it's going to go down like this, or it could go down as a curve, as a simple curve, or just whatever. It's not going to happen like this, but we know it's going this way. From left to right, it's going down. If it's increasing from left to right, it's going up. So let's see what's going on here. It's decreasing all the way to here, right? At x equals 0, because this is the x-axis. So it decreases from all the way over here, right? This goes on forever, so that's, you could say, it goes from negative infinity all the way up to 0. So all of this part right here is a decreasing line. Now, from 0 all the way up to a positive infinity, right, because this keeps going on and on. It's just a continuous function. From 0 all the way up, it's increasing, right? The function is increasing, going up. So what happens here? It's like it just stops. It's a point that it goes from decreasing to increasing. Now the derivative tells you something about this. Now 2x is like this. Okay? And that'll just be the point 1, 2. You see? So this one, let's just write it as f of x equals 2x. Okay? Now, original function, we look at it as decreasing and increasing. But when we look at a derivative, right? 2x is the derivative. When we look at a derivative, we don't talk about increasing or decreasing. Obviously, this is increasing the whole time because 2x is positive. Because if I just plot the points, that's what I'll get. So I just wrote the line 2x automatically. When we look at the derivative, we think about the position of where the line, the function, is located. So if you look, this function goes all the way from here to there. So we look at the y-axis now, right? So in the y-axis, remember, the negative side is here. All of this is negative. All of this is negative right here. All of this is positive on the y-axis. So the position of the derivative over here is negative. It's all negative from here to there, right? From 0 all the way to negative infinity on the y-axis. So from 0 all the way to negative infinity, it just keeps going down and down. It's going to be on the negative side. Now from here to here, that y, the position, it's positive. So from here all the way up, it's going to be positive infinity. From 0 to positive infinity. So if we look at the position, right, this is how you interpret it. If your derivative is on the negative side, then it tells you that your original function, your f of x, is decreasing, negative decreasing, negative decreasing. If your derivative is on the positive side, then your original function is increasing, right? And we can see the exact same thing going on here. Positive, increasing, positive, increasing. If your derivative is at 0, if it touches y equals 0, then your derivative, it looks like this. Your original function looks like this. Right? It's going to either, your original function is going to be right here or right here. The x part. So what does that mean? That just means that your original function is either at a minimum or a maximum. So here it's at a minimum, right? Because it's only at the bottom